Hello guys, welcome back. In this new video we will explore a new tool we have in Flubio, which is the mesh partitioner. This is a very good addition for our code since it allows us to decompose a mesh using our own tool without relying anymore on Decompose part, which is an utility coming along with OpenFOAM. So basically we retain the OpenFOAM format for the serial mesh, which you can obtain from any decent grid generator programs, both free or commercial. But this time, the decomposition of the mesh is done fully within Flubio without the need to load the OpenFOAM library anymore. So let's jump to a test case because I want to show you how to use this new tool. This is a simple test case, as you can see. We just need a read folder and a post-processing folder, and that's really what we need. Let's visualize the mesh we are gonna decompose. As you know, probably we have a command to do that, which is Flubio mesh view. We do not need anymore to specify the formats because now we support only VTK. So let's do like that. To visualize it, we can open ParaView, go into the post-processing folder, VTK fields, and we have a file called mesh.vtu. And here we have our geometry, which is a simple circle, and the mesh is triangular one with a very nice and equi-spaced triangulation. Okay, so how can we decompose this mesh in n parts in order to run later on in parallel? Well, we have set up this new utility, which is called Decompose mesh. So Decompose mesh is a bash script which wraps inside it several operations. It's worth to mention that in order to decompose the mesh, we use two external libraries. The first one is very well known and it's called Metis, and the other one is a bit more recent and it's called Kahir. So both of them are now into the libs folder and they are compiled along Flubio using the compilation script. And they are very easy to install, so if you are able to compile Flubio, you probably are able to compile those libraries as well, which will be ready to be used inside this tool. So this is the name of the script. We'll give you some more details in the meanwhile I go on with this tutorial case. If you want to find out the usage, then you just type -h or --help if you want, and as you can see you have all the explanation. A warning is important because this is quite new, as everything new it can be problematic somehow for some reasons. There can be hidden issues, but up to now it looks promising at least. So take in mind that probably this tool will be updated sooner than later because we are still testing it, profiling it a bit, and so on. But the main functionalities should stay as they are now. So let's explore a bit the options. We have a bunch of options. We have this one, -e, which stands for e-type. So e-type is a parameter used by Metis, and it can be 1 or 2 usually. By default we use 1. Then we have another very important parameters, which is minus s, which stands for minus subdivisions, which is the number of partitions you wanna create using this tool. Other ones are minus t, which stands for tool. So basically lets you specify which library to use for partitioning the mesh. You can use Metis and Parmetis, and if you wanna run in parallel, you can. And this you can use Parmetis or the parallel version of Caip, which is included in the library. If you run in parallel, you have to add to the command line minus p, so minus parallel, and also you have to specify the number of processors you are going to use to partition the graph, which is this minus n, or minus np. It's very worth to mention that number of processors you use in parallel and number of subdivisions can be different. So you can, for example, use 2 processors to partition in 8 parts. It doesn't really matter. So those two can be different. Just take it in mind. It's important also to clarify that when I say partitioning in parallel, it means basically that the graph or the mesh will be partitioned in parallel, which is considered probably one of the heaviest part, but all the rest, so the file creation and the file distributions for the different partitions are doing serially. This is because, of course, we need to know the serial mesh before partitioning it, and the process we use is basically this one. We read the serial mesh, we create a file, which is this one, called econ.msh. This file contains the connectivities for points to elements, basically. So element 1 is composed by verticals 1, 2, 3, 4, 5, 6, 7, 8. But element 2 by verticals, I don't know, 10, 11, 13, and so on. And we have a list of all the elements and all the connectivities with points. So this list is then converted into a graph using a utility we find in Metis. And then after that we have a graph. We can use or Metis or Caip to partition it. So the output of the partition is basically a file which presents n entries, and for each entry we have a number which corresponds to the partition number. This number, this list of partitions is then loaded in another utility, which actually computes where points, faces, and elements has to go in order to create a valid mesh to run in parallel. Then, okay, so this is more or less how it works. If you wanna look at the code, you can. So basically, just look for this name into the script folder. So it's all there. We do not hide anything. You can change everything as you like. So let's start this tutorial now. Let's say that you want to decompose this mesh, so we call this script, and then we start putting command lines. First, we specify the tool we want. Let's say we want to use Caip, and after that we have to specify the number of partitions. Let's say we want to use 4. If we run it, you can see it's doing a bit of logging. And what you get is basically some information printed to screen. You have the graph informations by Metis. You have the partitioning information from Caip, for example, this time. You can see, for example, the balance between partitions, the time spent for partitioning, of course. And then you have some other infos. For example, if you go down here, you see for some information which are processor related. For example, for this processor 2, you have this number of elements, this number of points, this number of faces, and then we have other informations which tells you how the partition is done, well or bad. This case, for example, we have 61 processor faces, so which are shared between processors, 0 and 2, between 3 and 2, we have 54, and we have the number of processor boundaries as well, which is 2, of course, because those are 2. And this is true for every processor. So now the mesh is done and it is decomposed. You may want to look into the grid folder just to see what happened. You see you have different files here. You have the processors folders that you need to run in parallel. If you try to list the inside things, you see you have all the mesh. But then you have also the different inputs and outputs we create for the decompositions. So this one is the first input, which is the mesh. In terms of connectivities, you see you have the number of elements and then you have all the points, okay, for the different elements, 1, 2, 3, 5, 6, of course, because if you look at the mesh here, you see that you have, yes, a triangle here, but then you have another one on the other side, so you have 6 points in total. And this is you see just a simple list like that. And after that you have the graph format. You can visualize it. You can Google it, or you can just look at the Metis, for example. Sorry, it's something not correct. So you can read the manual from Metis, for example. You see it's something like that. It's a bit different. It also contains information about edges, joining points. It's something we do not do. We just use the utility coming with Metis. And then the final thing we need is this file here. And if you look at that, it's just a simple work column file, but you see we used 4 processors, and now we can see that we have for each element 1 belongs to processor 2, element 2 to 3, and so on. So it's quite easy to understand. So how can I visualize the partitions? Because sometimes partitions are not good enough. We might need to check it in order to adjust some parameter. The easiest way is to run another utility from FLUBIO, which is mprun minus mp4, because you have 4 partitions. And then we use the parallel version of mesh view, which is called like that. And this utility has been updated in order to store the partitions colors as well. So if you run it, oops, sorry, typo para, okay, and then we can hide this one, open this one. If you go in parallel mesh, and then you see that we have the 4 partitions files for the mesh and a pdtu file which links them together. We just load this one. Same geometry, the same mesh, of course, but this time I can select cell list, and what I can see is the cell distribution I get from Kayip in this case. You see we have 4 partitions, and that's really it. Let's do another couple of examples. Let's change tool. For example, we use Metis this time. We change this, just do this, and run again. Okay, run again, and if we hide this, okay, and we load up the file again, we have this time distribution made with Metis, which is different, of course. You see, So the important thing is that the distributions of the cells is well balanced, because this way all the processors will have more or less the same load, and this will help the MPI to run better. It's also important that the processor faces as let's say not too much, because in this way we can limit the amount of MPI communications. Okay, let's do the last example. The last example will be decompose the mesh in parallel this time. So if you want to decompose in parallel, we have a flag for activate that. We can change to Caip again. I found the parallel decomposer of Caip quite good, so why not give it a try. This one remains the same, but this time we have to add number of processors we want to use. It can be 2, it can be 1, or it can be 4, because in this case I have 4 processors in my laptop. And after that, I need to activate the parallel mode using -p. So the graph partitioning we are gonna get is again different from the serial version. But the important thing is that the partitioning is well balanced. So you just have to try the way you like the most, and of course if you don't like something, you can tune the script by yourself by adding flags, by adding other things. For example, we have a flag here which is -v, which stands for variant, and variants basically are options you can give to Caip, and they correspond to different methods to partition a graph. So basically, in this way, you can get slightly different partitions. You can always read the manual of Caip or Metis to understand more. So everything is there, is also in here because we use those libraries. Okay, so let's run this in parallel. You don't need to do anything else. If you put -p, the MPI run call for Caip will be called inside the script. Okay, so we do not expect to see any particular speed up because the mesh is quite small. If we run it again, we hide this, we load it up, and we can visualize the partitioning. This partition looks quite good, to be honest. And if you wanna find different configurations, as I said, you can change variant or you can change the seed to start the partitioning. It's really up to you. What you get from the standard is usually good enough. Okay, so now we have played a bit with this tool. You can do your own tests. Let us know if you find issues into our GitLab page. Don't be shy. We like to know about bugs or problems or improvements we can do. The only thing that is left to do now is run your favorite solver, like that, for example. And it's all done in-house and within FLUBIO without calling anything from OpenFOAM anymore. We don't run it simply because we are missing the settings folder for the numerical options and so on. Okay, hope you have enjoyed it. Let us know if you find issues, and see you in the next video. Bye bye.